So let's finally talk about Newton's laws of motion. And so I'm just going to get right into it. The first law is often called the law of inertia, right? And so inertia is the idea that an object will resist changes to its motion, right? So objects with greater moments of inertia have a greater resistance to a change in motion, is one way that you can think about that. And so what actually does the first law say? Well, it says that an object at rest will remain at rest, and an object in motion will continue in motion with constant velocity unless acted upon by a net external force. Now that's a mouthful. However, I think it's a lot easier to just write it mathematically. So mathematically, we can say if the sum of the forces equals 0, then V equals some constant. Okay? So let's look at this. Sum of the forces. Well, this is just the net external force on an object. All right? So when we were drawing our force diagrams earlier, and let's say that this is a normal force and this is Fg, right? And this is just for a box sitting on a table. Well, in this case, we saw that the object is not just going upward, it's not just magically floating or crashing through the table. So we said that these forces must be balanced. And back then, we just kind of said that, right? We didn't really prove it. And so now we're actually going to say mathematically, well, N minus Fg is equal to 0 because of Newton's first law, right? Now we're actually attributing it to something. And so Newton's first law says that the velocity is constant. And well, obviously you might be thinking, well, the velocity is not constant, it's 0. Well, yes, it is constant. It's a constant 0 meters per second, right? And so this is something that you have to really come to understand thoroughly. The idea that an object can have a velocity that is a constant 0 meters per second, okay? So just like this box here on this table has a constant velocity, let me write that. V equals 0 meters per second equals constant, right? It doesn't change with time. That's all constant means. It doesn't change with time. And so that's what we learned from the first law, all right? So let's go over that one more time. An object at rest will remain in rest without some net external force. This box is just going to stay here unless we give it a net external force, Fa, all right, and there's nothing else acting in this direction, and so now the velocity is no longer constant, all right? Similarly, let's look at this example. Now, this one is less trivial than the box sitting on the table. Now, let's say that there is, let's do this actually. Let's do a ramp. And let's do a box on the ramp. And the box is sliding down the ramp, right? And so we know that this is actually some component due to gravity that's causing it to slide down the ramp, okay? I'm not going to draw the full force diagram here, okay? But this is just some component of Fg. This is Fgx, and this is our y direction, and this is our x direction, right? So we're saying our positive y is perpendicular to the ramp, our positive x is down the ramp. This is Fgx that pulls it down the ramp. And let's say that there's some friction force, okay? So let's just say, for the sake of argument, that Fgx is equal to F, all right? Now let's say that the box is also already in motion. What the first law tells us is that, well, we're saying in this problem Fgx is equal to F, so if you do that, Fgx minus F equals 0, then you can see that this box will move with a constant velocity. So let's say V equals 2 meters per second, okay? So if nothing changes, then this box will continue to, fall down this ramp forever and ever at 2 meters per second. And obviously, eventually something will change to cause that motion to stop. But Newton's first law says that until that change occurs, this motion will continue. And this is actually very incredible when you think about this. We live in a world where if you kick a soccer ball in a grassy field, it will come to a stop. Newton is saying that the only reason that happens is because essentially it's forced to, right? If it wasn't, if the forces were balanced, it would continue to move on forever. And so this is really truly an incredible discovery on his part. So then Newton's second law says that the acceleration of an object is going to be directly proportional to the net force acting on it, and also inversely proportional to the mass. And so what does that look like mathematically? Because again, that just tends to be the easier way. So acceleration is going to be proportional to the net force acting on the object, so F net, and inversely proportional to the mass. Okay, now I'll be honest, you're not going to really see it written this way very much, right? You are really going to see this form, where we say F net is equal to mass times acceleration. Or even more commonly, we'll just drop as tend to be lazy, we just drop everything and write F equals ma. And that is what you're going to hear over and over and over again. This is like the lifeblood of Physics 1. F equals ma. If you get stuck in a problem that is dealing with forces, then you probably need to just write F equals ma somewhere on the problem and go from there, right? That is just the best way to proceed in any problem dealing with forces. So you can actually see here, though, that this law, that the first law is actually a special case of Newton's second law, right? So in Newton's first law, the sum of the forces equals 0. So all we're saying is that if A equals 0, right, and I'm using the vector because the 0 vector is a true mathematical quantity and acceleration is a vector, so it must also equal a vector. So A equals 0 is the proper way to write that. So if A equals 0, then F net equals 0, right? And then the velocity must be constant, right? As we talked about with constant velocity, constant acceleration, we really hammered that down in some previous videos. And so when the velocity is constant, acceleration is 0. So V equals constant in this case. And that's just Newton's first law, right? One more time. So the second law is, as I said, the more important version. Finally, let's talk about the third law. The third law says that forces come in pairs, which are of the same magnitude but opposite direction. So mathematically, we might write it like this. The force from object A that acts on B is equal to the negative force from B which acts on A. And that is how you would say that. And it's kind of a mouthful. But let's talk about it like this. Let's suppose that object A is your left hand, and I'm going to draw boxes because I'm a physicist, and that's what we do. So left hand, right hand, right? And actually do this. If you're watching the video, take a second and stop and try and push your left hand against your right hand as hard as you can. And I want you to now understand, as you're doing that, that because of Newton's third law, your left hand can never push harder on your right hand than the force that comes in return. So in other words, as hard as you push with your left hand, the right hand pushes back with that same amount of force. All right, even if your arms, aren't deadlocked in the center, right? Let's just say that you let your right arm be a little bit weaker and you let your left arm kind of win, right? And you start pushing it to the right. Even in that scenario, Newton's third law holds true, okay? Now, there's a common misconception with Newton's third law. Many students think that, well, Newton's third law is confusing because it's saying that all of these forces cancel out, right? But they don't cancel out because when you draw a free body diagram, right, a lot of students are tempted to say, well, this is the force from my left hand acting on my right hand, and this is the force from my right hand acting on my left hand. But you can't do that. Free body diagrams are for one object, right? Not for the whole combination of your left hand and your right hand. So these do not, in fact, cancel by Newton's third law. Newton's third law is saying that you essentially have two force diagrams, right? This is the one for your left hand. This is the one for your right hand. Okay. Those two force diagrams, those are the ones that are equal. And so you just have to be careful in realizing that we're talking about separate objects here, right? Not the same object. And so I could go deeper into that, but I think that's sufficient. And so the idea here is that FA acting on B, right? That force, that magnitude is equal to FB acting on A, right? So the magnitudes are the same. The only thing that changes is that the direction is the opposite, right? So that's where that negative sign comes from. But you'll often see this form written, right? Where just the magnitudes are the same. So just keep in mind, again, if you're to catch a baseball, right, whatever force that baseball hits your glove with is the same force that you exert back on the baseball, right? If you were to, be driving in your small little Prius and you get hit by a big pickup truck or a semi-truck even, then whatever force the semi-truck hits your Prius with is the same force that your Prius hits the semi-truck with. And that might be hard to believe. And the real question here is actually a question of momentum, and that will come in a future discussion. But at that point, it'll make a lot more sense. Why of course the damage is so much more, awful for the Prius in this situation versus the semi-truck, right? But as far as Newton's third law is concerned, the forces on each vehicle are the same.